In this next module, I'm going to show you how linear regression accommodates categorical predictors, and I'll also show you the link between ttest and ANOVA and linear regression. So how does linear regression handle categorical predictors? In the case of a binary predictor, it's actually really easy. In the very first week of this course, I talked a lot about binary variables and thinking about them as 0, 1, as numerical variables. Well, that becomes useful now because the way that we handle binary variables is just to put them in the linear regression model and treat them as numbers, as a 0 and a 1. And that makes it easy to model, and I'll show you the picture in a minute. Categorical variables are just slightly more tricky. These are variables that have more than 2 categories. We are essentially going to turn them into a series of binary of 0, 1 variables, and that's the way we're going to accommodate them in the regression model. We call this dummy coding, and I'm going to get to this dummy coding idea in a few minutes. But let's start with the easier case, with the binary case. Imagine for a moment that I wanted to use vitamin D as a binary predictor. We've been talking about this example all week where I've been treating vitamin D as a continuous predictor. But there might be some reason that I end up wanting to treat vitamin D as a binary predictor. Maybe I didn't measure, maybe for some reason in my data set I don't have it as a continuous predictor, or maybe for some reason I'm clinically interested in comparing the insufficient group to the sufficient group. So for whatever reason, I'm using vitamin D as a binary predictor. If I look in my data set, and let's say this is sort of arbitrary, but let's say less than 15 animals per liter is some clinical reason for calling that insufficient. More than that, we'll call that sufficient. We're going to code this insufficient variable as a 1, 0. So if you're a 1, that means you're in the insufficient group. If you're a 0, that means you're in the sufficient group. And I actually looked in my data set, and the mean DSST score, the mean cognitive score in the insufficient group indeed was lower than in the sufficient group. It was 32.5, and in the sufficient group it was 40. Now you might just think about the lectures that we had last week, and you might say, oh well, here I've got a situation where I have a continuous, normally distributed outcome variable. I've got 2 groups I want to compare. I want to compare the means of that continuous variable between 2 groups. Why wouldn't I just use a t-test here? And indeed, you absolutely could use a t-test here. I'm going to show you how to also use linear regression to analyze these same data, and then I'll show you how the linear regression and the t-test actually give you identical answers. Let me graph this for you. So again, we're treating our binary variable as a 0, 1 variable. So 1 means you're in the insufficient group, 0 means you're sufficient, you're in the normal level group. The linear regression line here is the easiest possible line you can draw. So what I'm showing you here, these little individual points represent all of the DSST levels for all the people in the normal group. Their mean level is right here at 40. That was the mean in the normal group. The vitamin D insufficient group over here, this is all their DSST levels. Their mean, as I mentioned, was 32.5. So what's this line? All I did to draw this line was to connect the 2 means. It's like the simplest line you can possibly draw. Any 2 points, you can connect them and draw a line. And we don't have to test the linearity assumption here because when you have 2 points, it's automatically going to make a line. So that's nice. The intercept of this line, as you can see here, is 40. What's the slope of this line going to be? Well, the x variable only goes from 0 to 1. So there's only a 1 unit change in x. What happens to y when x goes from 0 to 1? Well, y goes from 40 down to 32.5. So the slope of this line is going to be 40 minus 32.5, or 7.5. Notice that that's just the difference in means between the 2 groups. I then took these data and actually ran them officially in a linear regression program, and indeed, not surprisingly, what I get out in the model is, here's my parameter estimates. So the intercept is 40, and the difference in means, the beta here, is negative 7.5 because we're decreasing as we're going from sufficient to insufficient. It's highly statistically significant, as you can see. This is just giving me back the equation of that line. We could also kind of look at the graph again to see the equation of that line. Again, the intercept represents the mean value in the sufficient group. The slope here just represents the difference in means between the 2 groups, and it is statistically significant. Now I want to show you what would have happened had we just run these data in a t-test rather than bothering to get fancy and run a linear regression. Well, we would have got the same answer. Again, we have 2 groups. We want to compare means. we can evaluate these data with a t-test. It turns out that the slope we get from linear regression is exactly equal to the difference in means, which is the effective size of interest for a t-test. And the p-values we get out are also exactly identical. So here's the t-test that we would run. We would, in the numerator goes the difference in means, again, which is 40 minus 32.5 or 7.5. We can calculate the standard error in the denominator. That turns out to be the same standard error that you get in the linear regression model on the earlier slide. The t-value comes out to be 3.46. The p-value comes out to be 0.0008. And actually, if you look at the previous slide, you can see that that is the t-value and the p-value from the linear regression. So there's nothing new here. Mathematically, a t-test and a linear regression are exactly the same. You could say we don't even really need to have a t-test in the world because you could always run that particular problem in linear regression. It's just, of course, that linear regression is more, seems more complicated. A t-test seems very simple, so a lot of times if we have the simplest problem, we end up just defaulting to t-test rather than calling it a linear regression. But in fact, a t-test is a special case of linear regression. Now I'm going to move to the more tricky concept, which is what to do when you have more than two categories. You have a categorical predictor with more than two categories. What we're going to have to do here is to do some dummy coding. We're going to translate our categories into a series of binary variables so that we can deal again with binary variables. So what if our vitamin D variable had been a categorical predictor rather than a continuous predictor? What if there were three levels we cared about? The deficient, that's like the really low people, insufficient, kind of mildly low, and sufficient. Sometimes people will divide it up this way. I want to know about the difference in DSST scores between those three groups. I could analyze those data then with an ANOVA, simple ANOVA as we talked about last week. And I also could analyze it with linear regression. So let me just tell you what the mean DSST score in all these three groups were. So the sufficient group, the normal group is still the same here. The average was still 40. The insufficient group now excludes the ones who are lower than 25. So the average in that group is now 33.13. And in the deficient group, it turns out that the mean DSST score is 30.13. So it does seem to go down across those groups. How do we dummy code this? How do we dummy code these three categories? So here's dummy coding. If I want to take a three-level categorical variable, I can represent it as a series of binary variables. I actually only need two binary variables if it's a three-level variable. If it was a four-level categorical variable, I would need three binary variables, and so on. There's going to be one group that's the reference group, and that's going to be the variable that has a 0 on all the binary variables. Let me illustrate that here. So I'm going to make two new variables. I'm going to create a new variable that is deficient, yes or no. It's binary. You're either in the deficient category or you're not. And another one, insufficient, that's a variable, another binary, that says you're either in the insufficient group or you're not. So if you're somebody in the deficient group, you're going to get a 1 on the deficient variable, but a 0 on the insufficient variable. If you're in the insufficient group, you're going to get a 0 on the deficient group because you're not deficient, but you're going to get a 1 on the insufficient. If you're in the sufficient group, however, you're going to get a 0 on both of those. So notice that two binary variables is sufficient to uniquely identify all three of those categories. Now we have a reference group and we have a series of binary variables that tell us about the difference between the deficient group and the sufficient group and the difference between the insufficient group and the sufficient group. How do we represent this in pictures? So it looks a lot like the pictures we did for the simple binary predictor. The insufficient group, again, the mean level of DSST for the insufficient group was about 33. The mean for the normal group is 40. That forms a simple line. The intercept is 40. The slope is about -7. For the deficient group, same intercept because we're still comparing against the normal group. The slope here, the mean for the deficient group was about 30, so the slope here is almost 10. Now technically this is a multivariate regression because we now have two predictors in the model. I could represent these pictures on a plane. It's just harder to draw that plane, so I've represented it as two separate graphs here. I took the data and I put them into the computer and asked it to run a linear regression with these dummy coded variables. And here are the results that I get. So here's my model. Here's my p-values. Again, the intercept represents the mean value in the reference group. That's 40. That's the normal group. The beta coefficient, the slope for the insufficient group, represents the difference in the DSST levels between the normal group and the insufficient group, the difference from the reference. So the insufficient group was about almost 7 units lower in cognitive score than the normal group. The deficient group was almost 10 units lower in the cognitive score than the normal group. So that's the slope for them. Both are highly statistically significant. That's the linear regression equation written out, and we can use that to then predict what's the mean value for those in the insufficient group, those in the deficient group, and those in the normal group. And you're going to see that for the simple model, it's nothing too profound. The 40 is the mean in the reference group. Negative 6.87 represents the difference in means between the insufficient and sufficient groups, and again, negative 9.87 represents the difference in means between the deficient and the sufficient groups. And you can just show this by applying the equation. So if I've got a person who's in the deficient group, how do I apply this equation to them? Well, they get the intercept, they get a 0 because they're not in the insufficient group, and they get a 1 for being deficient. So when you do 40 minus 9.87, that just gives you back out what we already knew was the mean in the deficient group. A person in the insufficient group, when you apply the equation, they get a 1 for insufficient, a 0 for deficient. When you add that up, it comes out to be 33.13. Again, what we already knew was the mean in the insufficient group. And the person who's in the sufficient group gets a 0 for both the insufficient and deficient variables, so they are just left with 40, which again we knew was the mean in the normal group. So it's a little like this isn't, it's just spitting back out the means. It doesn't seem all that profound. It doesn't seem all that useful. But the reason it's going to be useful is because we might want to adjust for other variables. ANOVA is just linear regression. So the p-value that you would get if you ran an ANOVA here is exactly the same as the p-value you're going to get for the overall model fit for linear regression. So again, mathematically, these things are identical. So when you could argue that you never need an ANOVA, you could always just run a linear regression.